and I'm really glad to sorry, I'm glad to share our recent preprint on the canonicalization diffusion. Yeah, so let's get started. Let's start with background and set up some notation. A 3D molecular graph series consists of atom coordinates x and atom features h, such that atom types and charge and bound features a. This leaves a magical space M. So the case structure is symmetry group G, the direct product of the permutation group Sn, which reindexes atoms, and the Euclidean group SC3, which rotates and translates coordinates. A group elements G acts on a molecular by simultaneously permuting atom indices and applying rigid transformation to coordinates. Two molecular related by any such transformation represent the exact same physical entity. And the orbit of Z is a set of all equivalent representations, and the quotient space M mod G collects all orbits. Each point in the quotient is a unique physical molecule. And for our idea here, a canonicalization map psi it selects exactly one representative from each orbit, satisfying two properties. The output lies in the orbit and it is invariant. Applying any group transformation before canonicalizing gives the same result. And this is the central tool in our framework. So now let me explain why symmetry creates a fundamental conflict for generative models. As I just introduced, a molecular admits many equivalent representations related by permutations and rotations. This is shown by the orbit on the right. We can see one molecular on the below is the original molecule we see, and in the orbit we can see pi from the Sn and r from the SO3 to either permute or rotate the molecule. And for diffusion and flow matching models, this redundancy creates three concrete problems. First, the trajectory crossing, and we can see the picture from our paper. As shown in the figure, when we add noise to a molecule and try to denoise it, the positional-wise supervision can point toward different equivalent targets, creating conflicting gradients. The second one is score function or velocity field becomes a mixture over all group copies. Essentially, a Gaussian mixture model with as many components as a group order. This requires more model capacity and smaller integration steps. A third, and perhaps less appreciated, the standard solution of building equivariant architectures comes with its own cost. Message passing GNs are probably bound by the 1WL graph isomorphism test, which limits what structural features they can distinguish and simultaneously requiring expensive specialized layers like tensor products. This leads to our central question. Can we break symmetry in a principal way, removing these difficulties and still guaranteeing that a general distribution is invariant? This is what canonicalization achieves. So before getting into our method, we can talk about the existing methods for handling symmetry in molecular generation. Uh, we can see this variance as a spectrum from fully encoding symmetry into the architecture to the right to explicitly breaking it. On one hand, equivariant architectures like EGN or EN equivariant flows build group equivariance directly into the network. This guarantees that the general distribution is invariant. However, These architectures are constrained in expressivity, as I mentioned, and they still suffer from gauge ambiguity, where the model must learn specific correspondences in the equivalent degrees of freedom. A recent some paper has shown that this invariance constraint can actually hurt performance by inducing mixture-like score functions. And in the middle, alignment-based methods try to heuristically reduce the ambiguity. A GOD lines and the clean structure to the noisy input, and AlphaFold 3 aligns training samples to the model output. More recently, SymDiff proposes stochastic symmetrization at sampling time, and RDM, I remember, learns a rotational alignment for non-equivariant backbones. These approaches reduce learning difficulty to uh, varying degrees. But alignment-based training is fundamentally incompatible with standard samplers. There is no guarantee that the sampling process recovers the correct target distribution. So our approach, canonicalization, sits at the right end of this spectrum. We map each molecule to a unique canonical representative on what we call the canonical slice. Train a standard diffusion or flow model on the slice and restore invariance at generation time through higher randomization. But this is both principle. We prove it eliminates the symmetry ambiguity term in the conditional variance, and practical. It allows us to use expressive non-equivariant backbones like standard transformers. In the next slide, I will explain exactly how it works. So this chapter is a theoretical spin of the paper. At a high level, it answers two questions. First, why is this canonicalization mathematically valid? And second, what can make it why can it make diffusion or flow matching easier? So now let me explain why canonicalization is theoretically legitimate. Our first result is a factorization theorem for invariant measures. It says that any G variant distribution mu can be exactly decomposed into a two-step generation process. Yeah. So first sample a canonical representative Z tilde from the slice distribution nu, which is simply the push forward of mu through the canonicalization map psi. A second, sample a random group element G from the higher measure independently, and output G times Z tilde. The resulting distribution is exactly mu. This is shown in the equivalent integral form below. Yeah. So the invariant measure mu can be written as an integral over the canonical slice S, where for each representative Z, we smear it across the entire orbit by integrating all the over the group with higher measure. This is not an approximation. It is an exact factorization. Yeah, from the figure we can see this process. So in a sentence, canonicalization is lossless for invariant distributions. We factor the invariant measure into a slice distribution plus higher randomization. The second result is universality. Given a canonicalization map psi and its associated gauge map kappa, where kappa recovers the group element that takes the canonical representative back to the original input. Any point x can be decomposed as kappa of x acting of psi of x. This decomposition lets us write any equivariant function phi into a factored form, kappa of x times f of phi psi of x, where f is an unrestricted function on the canonical slice. If f is a universal approximator on the slice, then phi is a universal for equivariant functions. So what does this mean in practice? It means the backbone network F does not need to be equivariant at all. Uh, it only needs to be expressive on the slice. The canonicalization map psi and the gauge map kappa handle the symmetry structure externally through the final randomization step shown here. Here I write down the final random to emphasize it. The canonicalization through the final randomization step here, equivariance becomes a property of the overall pipeline, not a constraint imposed on every layer of the network. This is what frees us from using standard transformer or any expressive architectures as a generative backbone. Why does symmetry actually make training harder? This slide answers this question. The key insight is that when the data distribution is invariant, the marginal distribution is at any noise time t becomes a mixture, a uniform average over all group transformed copies of the base density Q, as shown in the orbit visualization on the right. On the right, yeah. Uh, each equivalent representation contributes one component, and yeah, the consequent for the score function is immediate. The gradient of log p becomes a weighted combination of scores from each orbit copy, where the weights Wm depend on which group element best explains the current noisy state. When multiple orbit copies overlap, which is common at intermediate noise levels, these weights compete, pulling the score in conflicting directions. This is what causes trajectory crossing and makes the denoising problem fundamentally harder. So we come up with canonicalization. This approach collapses this mixture into a single representation on the slice. So the denoising geometry becomes much cleaner. In one sentence, in the ambient space, the model is effectively trying to denoise a mixture of symmetry equivalent words. On the slides, that mixture is collapsed into one word. And this is the most important theorem in this chapter. In flow matching, the irreducible regression error is exactly the conditional variance here at least for this line, and of target displacements given the intermediate noisy state, right? So the whole question becomes, why is this conditional variance is really large? The answer is given by a very clean decomposition, which I list here. Variance equals the within slice difficulty plus the symmetry ambiguity. And here's the formula. Under the lifted construction, the conditional variance splits into two parts. The first one, the intrinsic transport difficulty that remains on the canonical slice. The second is extra uncertainty caused by not knowing which symmetry frame generated by the observation. This second term is what we call symmetry ambiguity. And this is the real theoretical contribution. Canonicalization removes the ambiguity term. So for now, the learning problem becomes easier, not because all difficulty disappears, but because one specific source of irreducible uncertainty is removed. Here, the brief summary of the chapter. Uh, so, uh, as I mentioned, canonicalization eliminates the symmetry ambiguity term, but what about the remaining within slice difficulty? This term still depends on the choice of prior and the coupling. We show that an aligned canonical prior Gaussian matched to the mean and the covariance of the canonical data reduces this match, and the optimal transport further tightens the coupling. The key point is that these are complementary tools. And canonicalization removes the group ambiguity, while aligned priors and OT reduce the residual transport difficulty on the slice. Neither alone achieves both. And this is a figure from our paper. If you are interested in looking at that, you can see why these are complementary. So for the theoretical part, uh, to summarize this, first, canonicalization is exact for invariant distributions because an invariant measure can be factorized into a slice distribution and higher randomization. Second, canonicalization enables universal invariant and equivariant modeling without requiring an equivariant backbone. Third, so it improves learnability by removing the specific variance term. And our aligned prior and OT is complementary helping this process and is a good tool to for the residual size difficulty. Uh, so after the theoretical part, we immediately raises three practical questions. First, the factorization on the slides is pointing to what kind of direction that we can implement in engineer really. And the second, once we are on the slides, what kind of model can we do to actually train it? And the third, how do we sample from the slides and recover an invariant molecule in the end? So these are the three questions we answer in the method part of the paper. So firstly, for permutation symmetry, we propose a geometric spectral ordering, which is a fundamental method for graph operation. The idea is to build a geometry Laplacian from pairwise distances, which is rotational invariant, and then use the feather vector to induce a canonical ranking of atoms. Concretely, the canonical permutation is obtained by sorting the entries of the feather vector. It is geometry aware and it tends to preserve structurally meaningful neighborhoods. So this ordering acts as a principal molecular linearization of the graph. I provide two figures here. One is atheromorphism, which is high symmetry and contains microcycle. The spectral ordering is core-centric, concentrating the microcycle near the spectral center and mapping uh, peripheral sugar moieties towards the sequence terminals. And the second one is with a low symmetry. The spectral ordering unfolds along the principal axis from the polar head through the rigid core to the flexible tail. And once the atom order is fixed, the paper optionally fixes the rotational gauge as well. Yeah. So the idea is to use small set of anchor atoms selected consistently from the canonical order. Two anchors define primary axis, and the third defines the orientation of the plane, given a right-hand orthonormal frame. This yields a deterministic representative under the joint permutation and rotation action. And this is what we use to canonicalize the molecule. And after we enter the canonical pipeline, we do a training and sampling as our figure shows. And in the training uh, procedure, the simplest way to leverage canonicalization is through positional encoding. After mapping each molecule to its representative, we get a canonical rank and normalizing it. After that, we can use uh, any base model to train it. This is effective, and but can we do better by building canonicalization directly into the architecture? This leads to kind of flow. To fully exploit canonicalization, we designed Canonflow, a novel three-stream architecture that treats canonical rank as a first-class citizen alongside coordinates and node features. Yeah, so I think that the figure is pretty clear about how we treat the rank as a third components in the edge message network. And a critical component is auxiliary rank prediction head. During training, the model learns to predict the canonical ranks from its hidden representations. And at inference time, this enables dynamic rank estimation. The model can adaptively re-estimate the canonical ordering as a molecule is being generated without access to ground truth ranks. We find that predict mode works better than explicitly re-canonicalizing noisy intermediates because self-prediction integrates the canonicalization procedure into the model's own learning. Sampling follows the same logic as training. We start from a prior defined in canonical coordinates, integrate learn dynamics on the slice, and obtain a canonical sample. Then we apply a random symmetry transformation at the very end, which restores a fully invariant distribution. This is exactly the practical form of factorization theorem. So in our experiments, we show that on Q9, the most visible gain is geometry quality, with optimal RMSD improving from December to uh, uh, 0.17, together with a better convergence. And on geom drag, canon flow improves the key quality metrics over a similar flow baseline we selected. And most importantly, the advantage remains visible even at 50 steps with almost no extra sampling cost. So, faster convergence supports the claim that canonicalization simplifies the learning problem, and better few step performance supports the claim that the learn transport becomes straighter and less ambiguous. The small computational overhead supports the practical motivation for moving away from relying entirely on heavy equivariant machinery. Yeah, and I listed some future directions may apply this method to further enable us to explore the molecular war. And yeah, maybe it's around 30 minutes, right? So I can maybe
Yes,
later we can
yes.
discuss about this
Thanks.
part. Yeah,
Thanks. Thanks a
yeah,
lot. Um,
yeah.
yeah,
So yeah, this
now I
probably
think we have some time to, if some of you have some questions.